Have a seat, Mike. Get ready for the grueling questions here. So I'm also happy to introduce Mike O'Hearn, BC 61 from the Department of Physics. Apparently I heard on the way here he's a double eagle from BC High as well as from BC. And he was the project director or the principal investigator on pictures of what you've just seen. He'll be talking about a little bit called the Deep Impact Project from NASA. He's at the University of Maryland in the Department of Astronomy. He worked on this project for 10 years leading up to it. I'm reading off of the poster that's out front. And the part I liked and I wanted to read here, it's the first time that humans had touched a comet in space. Which is kind of cool. So as I said, he's a distinguished university professor at the University of Maryland, BS in physics at BC, a PhD in astronomy from, we'll forgive him for this, from University of Wisconsin, the Badgers. If you don't know what I'm talking about, you're not in tune with BC sports here. He's been at Maryland since 1966. He was at one point the acting director of the astronomy program and also the chairman of astronomy there for a while. And now he's a distinguished university professor. He's a AAAS fellow and several, more on the order of 100 publications. And a really interesting thing is he has his own asteroid. Asteroid number 3192 is called Ahern, named after, in honor of Dr. Ahern's contributions to the field. He's the PI, as I said, of Deep Impact, which we'll be talking about, also the principal investigator of a project of Small Bodies Node at the NASA's Planetary Data System. His life has been studying comets and asteroids at all wavelengths, which we'll describe as well, and associated with facilities all around the world. So welcome,
Thank
Mike
you.
Ahern. Take my captain's chair here.
Yes,
So, tell us all about it. No, I got some more specific questions here.
it was fun. What more do you want to know?
I have prepared some questions. I'm going to try and get through my list of questions, and then we're going to open it up to the audience for any questions you might have that I didn't cover as well. But the obvious point is to start with Deep Impact, and who had the name first, you guys or the movie? That was a joke.
Actually, the movie did. We and the movie came up with it independently.
I see. So no one has the rights.
And they copyrighted it before we used it publicly, but
Okay. So basically, just tell us about, describe the whole project and what were its significant scientific findings.
well, in very simple terms, the project was justified as throw something at a comet and see what happens, which sounds pretty dumb, except when we first proposed it, everybody in the science community said this is really stupid because we know exactly what's going to happen. And we did actually find 3 people who claimed the same thing would happen, i.e. everyone knew what would happen, but they knew 8 different things. So that was the real justification. We wanted to understand what's the difference between the inside and the outside of a comet, because the inside preserves a record of the formation of the solar system. And what we normally observe is the outside, so we want to be able to interpret all the data we have from Earth on comets. So this was a NASA mission, PI-led mission. It's a series of missions where a science PI, typically from a university, is in charge of the whole mission, and a NASA center works for the PI rather than the big missions like Cassini, where the center leads the mission.
Excuse me, is that kind of a new thing, or is that a normal thing, or was it?
It was something that started just before Dan Golden was at headquarters. It was started by Wes Huntress when he was at headquarters in order to get better cost control over the missions and to get more frequent opportunities to fly into space.
So how much was known about what asteroids and comets were made of before, and how much have you learned after? Do we now know what they're made of, more than we did before?
We certainly know a lot more than we knew before. Some of the key things that we've learned are that the gas that comes out and that you could see in principle from Earth comes from different parts of the comet. Carbon dioxide comes out of one part, water comes out of a different part. And that probably tells us that 4.5 billion years ago, when we brought little cometesimals together to make comets, we brought together parts that were formed in at, say, Uranus, and other parts that were formed way out beyond Neptune, where it was colder and there was more dry ice. So we had different pieces of very different compositions coming together to make the comet. So that's probably one of the more interesting results so far. And that came before there was an impact. That was on approach. And as I said at a talk at lunch, there was a great book by Martin Harwitt 10 or 15 years ago on discoveries in astronomy, pointing out that all the arguments you use to sell a big project, it's going to perform this great test, it's going to give us this great conclusion, all of those results typically pale in comparison to the unexpected results from looking at a whole new wavelength range, doing a whole new kind of experiment, looking at a new regime of spatial resolution. So doing something new in a totally new regime usually leads to surprises. And we certainly had our share of that just from looking intensely on the way in, even before we did the impact. From the impact, the kinds of things we learned are that the comet is mostly empty space inside. We could measure the gravity, and we measured how big it was, so we got a mass and a density, and it's 80% vacuum inside, 20%, 30% material. We learned that it's got about the strength of talcum powder. So we have something that is no strength, almost no gravity, but it's held together by gravity. And even in this zero gravity environment, we have geology taking place on the surface. We have features that look for all the world like terrestrial geological features. And we sure don't understand how that happened, but those are the kinds of surprises that come out of this, and I'm counting on at least 5 years of data analysis to understand what happened.
So you said it was held together by gravity. If it wasn't gravity, what were the ideas that would have been holding it together?
Well, it could be strength. And
Elaborate on that a little bit.
if you look at asteroids, for which we have a lot more data, most of the asteroids are held together by gravity and they rotate slowly. Only the really small ones rotate very rapidly, and they rotate so rapidly that if they were held together by gravity, they'd fly apart from centrifugal force. And so the small things in the asteroid belt, and small means less than 100, smaller than a football field, those things are held together by the strength of the material. So the material really is strong. The cometary nuclei, as far as we can tell, are all very weak, but we haven't measured it in any way for most of them, and only for Temple 1 do we have a really good firm number on the strength. So the strength is of no importance in holding it together. Fortunately, it rotates slowly, so centrifugal force doesn't cause it to fly apart. And even the tiny gravity can hold it together. The gravity is so low that you could walk off the asteroid into interplanetary space. You wouldn't even need a running start. It's just a fast walking speed is the escape velocity.
So why did you choose Temple 1? Well, I guess I'd like to know where it got its name, and then why did your team, you or whatever, choose this one to look at? Is it typical? Do we even know if it's typical?
The comet got its name, Temple 1, because it was first discovered by Ernst Wilhelm Leberecht Tempel. That's why it's Temple P-E-L, not P-L-E. And he was a German. He grew up in Niederkunnersdorf, which is on the border between Germany, Poland, and Czechoslovakia, where they come together. He was a lithographer, primarily by trade, and when he discovered the comet, he was actually working in Marseille, France, as an astronomer at the observatory in Marseille. He discovered a number of comets. This is the first short period one that he discovered. We picked it largely because we thought it had a large nucleus, which was important. And other than that, we could get there with the right geometry. We could have a high encounter speed. We could approach it from the sun side instead of the dark side. And we could get there with minimal energy on a short trajectory. So mainly it was geometry. In most respects, it's a very typical comet. Its chemistry is a little bit unusual. It's missing certain kinds of carbon chain molecules in what normally outgasses. But other than that, it's a very typical comet of Jupiter's family. Comets that formed out beyond Neptune, pardon me, and have been captured and brought in to where they're now controlled by Jupiter. And there are probably 150 such comets known, and this is a relatively average one, and that's what we wanted, so that you can observe one and say, well, it must be true for all, which is a great extrapolation, but until we do a second experiment, what else can you do?
So you had the main ship, I guess, that we saw in the animation. We saw an animation of it, and that had the module that went down and hit the comet, and then it took pictures of it, right?
Right.
What was the mechanism by which it, went down? How long was it traveling between when it left its, what do you call the flyby?
Yeah.
When it left the flyby, and the impactor is the other one called? Yeah. So when the impactor left the flyby, was it like 5 minutes or a month or what? How long did it take to get there, and what was that?
Yeah, we actually had 2 complete spacecraft, fully functional, 3-axis stabilized with electronics, radios, a camera, and so on. The 2 flew as one until a little bit more than 1 day before impact. So 1 day before impact, they were lined up more or less to hit the comet as best we could from that far away, and they separated. After they'd been separated for 2 hours, the impactor took over its own navigation and did a few maneuvers to ensure that it hit the comet in a sunlit portion on the side where the flyby was going to go. The flyby then slowed down enough so that it could watch for 800 seconds before it flew by. We're going by at 10 kilometers a second, so you've got to do everything very quickly. Everything was done entirely autonomously from 36 hours out. In principle, we had the capability of telling it what to do in real time, but we were terrified of doing that because you have to have thought through in advance everything you would want to tell it, and if you're going to do that, you may as well program it to do it by itself.
So how many people were involved in putting this all together? And you were the PI, the principal investigator, and maybe tell us a little bit about what that entails. What's it like to be the PI?
I generally tell people that being the PI on a mission like this is a wonderful thing to have done. It's not much fun when you're doing it. It's a major challenge. This mission, it took us 5 years to sell it, to convince other scientists that, on review panels, that it was worth doing. And then it took us 5 years to build it and fly it, and I'm counting on at least 5 years to analyze the data. During the selling phase, we were doing science. During the construction phase, I basically stopped doing science. I was doing engineering management. I learned more about engineering than I ever wanted to know. I learned more about personnel issues than I ever wanted to know. And basically, the PI on these missions is responsible for everything. If something goes wrong, the PI is the first one who gets yelled at by NASA headquarters. And that happened to me more than once. So it's a lot of work. It's a real challenge. It's a great payoff at the end. I mean, we've got tremendous scientific results. I'm thrilled by what came back. I'm having a really fun time analyzing the data. So it was worth doing, but as I said, a wonderful thing to have done. Now, there are people that like the management side. For them, it's fun to do it. For me, it wasn't. For me, the fun was the payoff after we hit.
I thought an interesting part was you had, you can tell me how many, but you had basically all the world's satellites that were capable of looking at this, all pointed toward it at the same time. Yeah. So these are from how many different countries have agreed all to participate in this 800-second event?
Okay, I'm not sure I can. I've never actually counted up the countries, but probably 25 or 30 countries had facilities participating in observations of the event. One of our science team members was assigned to coordinate all all the telescopes in the world, both on the ground and in Earth orbit. We even had the European Rosetta spacecraft. We had Spitzer Observatory, which is in an Earth trailing orbit around the sun.
You had Hubble.
And we had Hubble, which is in low Earth orbit. And basically every facility in the world of any significance was observing the events because it was a unique opportunity and because everyone realized we couldn't predict what would happen. We didn't know whether the best results would come from radio telescopes, X-ray telescopes, optical telescopes. It was very hard to predict. So every technique was applied, and basically there were scientists in every country that wanted to do it. They all did it on their own funds. We didn't pay them.
So the flyby ship, the mothership, I guess I'll call it, where is that now? Is that useless, or is that still hanging out there waiting to do something else?
At the end of last July, we put the flyby spacecraft onto a trajectory to bring it back to Earth, or close to Earth, not to Earth, and then put it to sleep. We woke it up in February of this year. It said hello, and we put it back to sleep so it could go around behind the sun where we can't talk to it. And it'll come back close to the Earth on New Year's Eve of 2007. And we have a proposal into NASA to use that approach to Earth for a gravity assist to take us to another comet to do a flyby and do the same kind of observations of this other comet that we did on approach to Comet Tempel 1.
Very good. So let me back up a little bit now. You're a kid from Braintree, you go to BC High, you go to BC. Between there and being principal investigator at the first thing humans ever made to touch a comet, walk us through that a little bit. I guess graduate school will be next,
Right.
and what was your, maybe some advice for the present undergraduates and even graduate students in the audience. What was your thought process along that trajectory?
At high school, as you said, I went to BC High, which is primarily a classics high school. We were allowed to take 2 science courses in 4 years. So most of my training was classics, but I decided I wanted to go to college in science. It wasn't obvious what science, so I picked physics. I sort of liked that. By the time I got to be a senior, there were a whole bunch of us that year that were put into the first year graduate courses in physics, and I got really bored by theoretical physics and said, I want to go to graduate school in something that's more applied or experimental, building things or something like that. So I decided to apply to graduate school in astronomy, and that I found I did enjoy. Astronomy is just applied physics. And it actually turns out that my entering class in graduate school at Wisconsin, turns out I had the best physics background of anyone in that entering class coming out of BC, which surprised me when I got there because BC wasn't known as a science school.
It's a powerhouse now.
Yes.
So funny.
I graduated at a good time. In the 60s, there was such a panic about the Russians that every university in the country was trying to build up astronomy and physics and several other sciences so you could go straight from graduate school to tenure track jobs. That stopped 4 years after I got out. So I went to Maryland on the faculty and figuring I'd probably be there 5 years, but they left me alone to do my own science, which made me happy, and they gave me tenure, so I just stayed. And the real thing was, in most of my career, I did ground-based astronomy, going to telescopes, observing comets, observing asteroids, did some work on just interstellar dust, things like that. And a significant part of the really big conclusions in my work have come from being in the right place at the right time and knowing how to seize the opportunity. Discovering new molecules in comets, just because we saw this comet was coming very close to Earth. We had a target of opportunity proposal to use an ultraviolet spectrometer in space. They gave it to us. We discovered new molecules that are really important for understanding the formation of comets. And a key thing was knowing how to be in the right place at the right time to do the interesting observations. Astronomy is very different from most sciences. You think of physics or chemistry or biology, they are experiment driven. I mean, you do theory, but you also do experiments. Astronomers don't do experiments in general. Astronomers let God do the experiments and observe passively what happens. Deep impact was one of the really few experiments in astronomy. There have been hardly any. The last big experiments in astronomy were throwing Saturn rockets and lunar modules at the moon to understand the seismic properties of the moon, using the seismometers that the astronauts had left behind. So bringing real hard experimentation to astronomy was a real opportunity when NASA had this, opened up this program of PI-led missions. It's the kind of mission that would never make it through center-led things, because center-led missions try to satisfy such a huge community. These PI-led missions, you pick your science team from wherever you want to pick them, and you do a relatively narrow focused program. And again, that was a matter of just being in the right place at the right time to get this through, and recognizing the opportunity of something that I thought at the time would be fun. And although it wasn't fun for the 5 years of building, the payoff has been great fun. And the whole interest in doing it is because of curiosity about how things work in the universe, and figuring that out is fun.
So curiosity plus serendipity plus preparedness.
Yes.
Remember that.
The
So-
preparedness is important. And I have to say, my senior year, I took this very high-level theoretical electricity and magnetism course. I hated it. I never wanted to see it again. 20 years later, no, less than that, 10 years later, 10 to 12 years later, I was building an instrument, and I had to sit down and go through the electromagnetism of waves going through a birefringent crystal. So it really paid off. Having had the background was important, even though I didn't like it at the time.
So of the things you do nowadays, which include lecturing, whether it's undergraduate or graduate, being out at the telescopes looking at what's up there, or in the lab preparing the next launch or whatever, or at events like this, or even maybe on national TV as a spokesperson for a NASA program, what do you like best about each of those, or what do you like best among those, and what are the challenges for each one? The teaching part,
Okay.
the fun part, research, and they have to explain it to everybody to get the money.
The teaching part I love. Provided I'm teaching a class where the students want to learn something and are not solely there because they need 3 credits to graduate. I actually enjoy that a great deal, as long as there's give and take between the teacher and the student. I despise grading, however. That part of teaching is not fun. The staircase method just doesn't work. Doing the science, I used to love being at the telescope. That was the best part of doing science for many years. I haven't done it in recent years. Too many trips of getting altitude sickness at the top of Mauna Kea. And just not having had time to do it over the last 6 or 7 years. I just haven't had time to go to the telescope anymore. I probably would enjoy that if I got back to it soon, just as much. Being a spokesman on television, I don't mind it, but it's not something that drives me. What drives me is being able to figure out the science and get the science papers written. To the extent I can then explain that to the public, that's important. But it's getting the original understanding that's the key point for me.
No, but you've probably had to go before Congress and explain why they should you know, to justify some portion of the NASA budget? And is that
I've actually
have
never,
particular challenges?
I've actually never done testimony before Congress, although I have met occasionally with congressmen in their
I
offices.
see. Okay.
I have had to go before NASA and, you know, National Academy NRC panels a number of times. I don't
There
do-
you know you're talking to scientists in general.
Yes, exactly. That's different from talking to politicians. I don't do the politics very well. I leave that to people who do it well.
That's fair enough. Yeah. What kind of advice might you have for the undergraduates in the audience here, or the graduate students that might be interested in astronomy for professional careers, whether it be for graduate school or for they want to work for NASA or they want to start their own companies, or what kind of advice might you be able to offer?
Well, if you're thinking of doing any of those things, except maybe the one of starting your own company, you better be thinking you want to do it because it's fun to do it. Because you're not likely to make money at it, at least not large amounts of money. At my stage of my career, I'm actually paid very well, but it was a long time before I was paid well, in any sense of the word. So if you want to go into science, working for NASA, working for a university, academic scientist, some other lab scientist, you've got to go into that because you enjoy doing the science. And that's the way you will be good at it, because you have the curiosity that drives you to be there. Now, starting your own company, that's a different matter. I've thought about that. And there, knowing the science is still important. And curiosity is still important, but the motivations tend to be somewhat different. Unless what you're doing is starting a company to solve a particular scientific problem. That's very different. Then you're really driven by the curiosity. So it depends on what kind of a business you want to start, what your motivation needs to be, and where you ought to be going.
Well, for your project, say Deep Impact, didn't you have to, I'm guessing that you had to contract with a variety of companies, large and small, for specific aspects of the program? Are these companies that are specifically work for NASA, or they have government contacts only, or how does that work?
Basically, we put together a team that consisted of Maryland as the PI institution, Jet Propulsion Laboratory in California to do the project management and the operations, and Ball Aerospace in Colorado to build the spacecraft and the instruments. So in that sense, the contracting for me was relatively simple. We just set up the original agreements, and that was in the proposal. And then either JPL or Ball Aerospace, they had to subcontract with a lot of other companies to get pieces. And, for example, the vendor of solar cells went bankrupt after getting 3/4 of the funding and delivering only 1/4 of the solar cells, which is a typical problem in the aerospace industry. The vendor of the gyroscopes tested them harder than they were ever supposed to be tested, and the welds cracked. And we frantically argued for 6 months over whether it was safe to fly the gyroscopes. We and the Messenger mission were using the same gyroscopes with the same problem. So there are a lot of engineering challenges like that, and there are so many of them that basically a PI alone can't make those decisions. And you need to hire experienced engineering managers to make most of those decisions, even though the PI is ultimately responsible for what happens.
Okay. I have a couple more questions. I want to go back to Temple 1, and I think we'll open it up to the audience if they have questions. You said it has the strength of talcum powder or something?
Yep.
Does that mean that it had, like, the density of it? Was it just loose dust, or was it like the density of
Yes.
chalk? Or
It was probably fluffier than talcum powder on Earth because there's no gravity holding it down.
yeah, okay.
It's definitely not the density of chalk. That's much too dense.
So it really wasn't outrageous for some of the people who didn't most people didn't know quite what to expect, to think it might actually fly right through it, though.
Right. Yeah,
That was one of the possibilities.
I was seriously worried, not so much that it would fly all the way through, but that it would just tunnel and make this, the impactor was about 1 meter in diameter. So it would just fly in, make a 1 meter tunnel 150 meters deep, and no crater.
So nothing.
That was the output,
Yeah.
that was the outcome that had me most worried during the whole event, and hoped we would be able to see that 1 to 2 meter hole to know that that's what happened.
How deep did it go then?
We think it went about 20 to 30 meters deep. It turned out that all of the material that came out in much smaller particles than we expected. Because they were really small particles, it was about the same amount of mass we had predicted. Because it was all in small particles, the cross-section to mass ratio was huge, so we never saw through the cloud of debris before we flew by. So we never actually saw the final crater. And that was the one thing that we missed out on in the entire experiment.
Well,
But we think the crater was probably about 150, 200 to 250 meters in diameter, and something like 30 meters deep.
So someday, we might be able to go look at it again, right? It comes around
Yes.
every 5 years or so, right?
Right. Comet comes back every 5.5 years, and we've also submitted a proposal to NASA to take over the Stardust spacecraft, which just brought the samples back from Cometville 2. We want to take that over and send it to Comet Temple 1 in January of 2011 and look at the crater that we made at this apparition.
Are there any questions from the audience? Yes, there are. There are several, I'm sure. Dr. Kelly.
If the comet's held together by gravity, but it's mostly empty space inside, why doesn't it collapse on itself?
Gravity's pretty weak.
But it's got a long time for it to act.
Yeah, but it basically just requires a really weak contact between adjacent grains to hold this grain up.
So in 4 billion years, it's not compressing on itself.
Right.
Yes, Dr. Madhavan.
So, what's the probability in its 5.5 years of orbit that another object is going to hit it?
It's not zero, but it's not very high.
It's small, I guess.
Right. And one of the surprising results is that there's a large number of features that look like they could be impact craters. We expected some. The large number is surprising.
So do you expect comets to accumulate, once they've accumulated enough impact, do they fly apart, disintegrate? Or it doesn't happen for hundreds of thousands of years?
It doesn't happen very commonly. Comets do spontaneously break up. Maybe, as comets come in close to the sun, there's probably a couple of % probability that any given comet will break up spontaneously. Right now, there's a comet called Schwarzmann-Wachmann 3, which is coming to perihelion this summer. And at its previous apparition 6.5 years ago, it broke up into 3 or 4 pieces. It's now in 20 pieces, some of which clearly separated within the last couple of months. So this is spontaneous fragmentation, probably driven not by impacts, because it's several separate events, and there can't have been that many impacts, but driven by volatiles warming up enough to blow it apart from the inside.
Yes.
For this whole project, how many people involved and what's the total budget?
At the peak of construction, there were about 300 people working on the project. During operations, there were maybe 75 people, during flight, there were maybe 75 people working on the project. Total budget when we put the comet to sleep at the end of last July was $332 million.
Was it very close to the original proposed total cost?
The cap we proposed to was 300, which is actually pretty close. It's closer than the missions, than the follow-on missions are.
Closer to the big dig.
Yeah, exactly. Yes, we are better than a factor of 5 or whatever the big dig was.
I have to believe that the impact portion of the module is somewhat hardy, given that the Comet is like talcum powder. Have you lost contact with that?
What happened to it?
The impactor, right after impact, actually if you'd seen the other movie, there's a really fast puff that comes out of really hot material. So when the impactor goes in, it comes in like this, tunnels in obliquely, it came in at about 30 degrees, and got to 30 meters deep after whatever the corresponding horizontal thing is, 100 meters or so. When it stops, you actually vaporize part of the impactor, vaporize some of the target, and based on experiments we've done in the laboratory, you probably melt the remainder of the impactor and it's buried down underneath the crater. But some of it, that first hot material that came out was the vaporization of part of the impactor and part of the target.
Now, do you know that because of your imagers could tell what materials came out?
Yeah, we have spectra of the material coming out and we can actually measure the temperature. So the material, there was a puff of material of order a ton of material that came out really fast and had a temperature when it moved in front of our spectrograph slit of 1500 Kelvin. And if you model that, it probably started at 3000 Kelvin when it was below the surface, blew through the top. 1 second later, everything was cold. It was below 500 Kelvin. It might have been at 300 Kelvin.
And what was in that?
And that was something like 10,000 tons of material came out from a 1/3 of a ton impactor.
What was the material that came out? Was like the elements of
It was
steel or
everything.
something?
No, it was, there were water ice crystals that came out.
No, I mean, sorry, the initial plume there.
Oh, the initial plume. No, the initial plume, because at that temperature it was all gas. Well, it wasn't all gas. There was what we could measure directly in situ. There was water at 1500 Kelvin, hydrogen cyanide at 1500 Kelvin, carbon dioxide at 1500 Kelvin, and something else that produced a black body spectrum at 1500 Kelvin, which we've modeled as tiny liquid droplets of silicate, but might have been something else.
So it's still there, but probably can't be woken up.
Right. And there are no pictures coming back from it anymore.
Earlier you mentioned wavelength with respect to comets. Can you explain what you mean by that?
Wavelength.
It might be the wavelength at which you're looking at it.
Oh, yeah, I mean, we observe comets at a wide variety of wavelengths of electron, the passive observations. You try to use every possible wavelength from X-rays through the ultraviolet, the optical, infrared, submillimeter, up to the radio regime. I've personally used most of those techniques except X-rays. From deep impact, we used optical wavelengths for all our imagers, and we used near infrared for the spectrometer. That's limited by how many instruments we could afford to put on.
It's probably too early to ask this, but has there been any new discoveries found from the impacts?
The significant new discoveries, I think, are the very weak nature of the material, the extremely high porosity. It's an average density of 0.35 grams per cubic centimeter. Ice would be a little under 1. Silicates would be 3 or 3.5. So that implies really high porosity on the inside. So I think that's a significant result. The fact that the carbon dioxide and the water spontaneously come out of different places is a significant result that tells us about the mixing of the cometesimals. The fact we've measured the response of the surface temperature to sunlight and deduced that the heating from sunlight doesn't go more than 10 centimeters deep. The ice, there is ice on the surface, but that's not where the outgassing comes from. All the outgassing that we see, lots of water. Water is the most abundant volatile on comets.
This is the tail we're speaking of.
Well, the coma, the head.
Yeah,
Okay. And that all comes from somewhere below the surface, but probably less than 1 meter below the surface. Whereas previously there were theoretical models that said it came from somewhere between 10 centimeters below the surface and 500 meters below the surface, because the models were unconstrained by data. Now we're pretty sure it's all within 1 meter of the surface. So that's a few of the key results.
Yes, over here.
What are the implications then on the current theories of the formation of the solar system?
The most significant one that we can understand is the fact that the different parts of the comet have different chemistry. And that tells us that 4.5 billion years ago, when we made the comets, which was before we made Jupiter through Neptune, because the comets formed the cores of those planets. When we were making the comets, we were bringing together things that were not in circular orbits, but were in eccentric orbits. So we were bringing things from a range of distances from the sun together to make the same comet. So that's one important thing. The other significant result for the formation is that you have to bring these things together. All the theoretical arguments in the past have said out in the Kuiper Belt things should come together at 1 or 2 kilometers per second. You've got to bring these porous things together at 1 or 2 kilometers per second and keep that very high porosity. You can't collapse them when they come together. You have to keep them apart and porous. That's understanding how to explain that is a challenge for the theoreticians. I don't have an answer for how we're going to explain it, but it's an important constraint.
What was the projected success rate of the whole impact, and throughout the mission, how confident as the PI were you that we were actually going to hit this asteroid?
I was very confident. I was actually never very worried. The navigators, whose necks were on the line, were really worried. I was far more worried about the uncertainty in the physics because of the lack of knowledge. I was worried about the tunneling in, but I was never very worried about hitting it, even though the navigators kept telling me how worried they were. But they did so many simulations and statistical analyses that I actually had very little worry about that.
When you say that 70 to 80% of the comet was vacuum, what do you think the geometry of it was? Like huge expanses of vacuum or smaller pockets?
My hunch is very small pockets, but I don't know. We have no way of constraining that directly.
So now if one's headed towards Earth, do you have any idea if we can blow it up or move it or anything?
We have not yet figured out the mass that came off at different velocities. We're still working on that. That's what tells us how efficient we would be if we tried to do an impact to change the course. What's the momentum transfer efficiency? You know, it's more than 1, but it's unclear whether it's 1.5 or 5. But that is something we will get eventually with a little more detailed modeling of the ejecta. I think the surest way of preventing a comet from hitting us is to basically deploy a huge solar reflector that focuses sunlight on one side and causes a jet that naturally drives it away. If you hit one of these, if you divert one of these things long before it's supposed to hit the Earth, it doesn't take much change to make it move by half an Earth, by 1 Earth radius 10 or 20 years later. If you do it at the last minute, it's incredibly hard. So the real trick is to find them early.
So are we looking sufficiently deeply, densely?
For the periodic comets and the asteroids, yes. For the non-periodic comets, no, because we don't know how to look for them early enough. And they're the ones that are the hazard that is most difficult to predict.
Oh, I saw some other hands.
You mentioned that you identified some new molecules from the impact, I thought.
Well, no, not quite. There are many new spectral features for which we have not yet identified the molecules. We're still working on that. We don't have very high spectral resolution, which makes it hard to pin down a unique identification unless you have multiple features and can get the right intensity ratio.
Are these like hydrocarbons, or you don't even know?
Well, we know there are hydrocarbons there, but we've known that for a long time. There's methanol, formaldehyde, acetylene. We've known all those things are there. But there are clearly new ones that are probably more hydrocarbons or organics. They're in the same spectral range where you get the carbon-hydrogen stretch feature.
Since you're sort of on the topic of organics, now there's scientific theories out there that perhaps life was brought to here, or water was brought from these comets or bombardments of the comets to Earth, and that's where the origins of life might have stemmed from. Was there any concern, or did you put the spacecraft through any kind of sterilization or purification process to avoid contamination of this comet? Like you said, there's an impact, but there might be some of that spacecraft from the impactor still left lodged in that comet. Was any concern paid to, whoa, we don't want to contaminate that and possibly, take life to someplace else?
There is no particular issue with taking life to someplace else like a comet, unless you think that's a place you're going to want to go to look for life. So if you want to go to Mars, you've got to sterilize things, at least if you're still using the argument that you're searching for life. If you want to go to a comet and search for life, you just go to a different comet than the one we contaminated. The point is there are lots of them. So no, we did not spend a lot of effort on that. We had the appropriate approvals. NASA has a whole approval process from the Planetary Protection Office. And they approved us to go without sterilization.
Over here?
If there's nobody else. Okay,
Go ahead, we'll get to it.
okay. I just wanted to ask about the tail of the comet.
Mm-hmm.
What holds what holds it together actually?
The tail? It's not held together.
But it's loosely, but
The-
there's a collection of objects.
The comet is losing material. Okay, so you've got this nucleus that's sort of the size of Boston. You have ice is evaporating, mostly water ice, apparently a lot of carbon dioxide, more than we had realized, because carbon dioxide is hard to observe from Earth. Some carbon monoxide, a bunch of other, some methanol, a lot of volatile things. They spontaneously evaporate when you get near the sun, provided they're close to the surface. When the gas comes out, it drags the small dust particles with it. Okay, so that just gives you a spherical head or coma for the comet. But that's expanding away to infinity. Some of the gas gets ionized. The ionized gas interacts with the magnetic field in the solar wind and gets driven back into a really straight ion tail, well, a long, more or less straight, sometimes it has funny kinks in it, tail. The dust particles are driven back into a separate tail by solar radiation pressure. So the dust is being driven back into the tail. That's ultimately the source of the bigger parts of that dust are ultimately the source of most meteor showers. So they're dissipating gradually, but they remain more or less coherent over many orbital periods, and that's why we get recurrent meteor showers every year when the Earth goes through the orbit of a comet. But ultimately, all that material is leaving the comet. It's not being held together. It just takes a long time to go away.
Eventually the comet should just die.
Yeah, it's losing mass all the time.
It's losing mass all the time. There's a fair bit of evidence, however, that for some reason, comets turn off and stop evaporating before they run out of ice. We see a lot of things in orbits that look as though they have to be comets. They're all really black, just like comet nuclei. They have no fuzz around them, no outgassing. So they're probably comets that have turned off. And that actually was one of the things we were trying to test do the comets turn off because they run out of ice? Or do they turn off because the ice just got buried under some layer that seals them in? And it's not, I think it's not, after a deep impact, I think it's not a layer that seals them in like organic glue, but just a thermally insulating layer of dust that is such an effective insulator that the sunlight, once the ice gets far enough below the surface, heat just never gets down to evaporate it anymore.
Okay.
One back in the
You had one
I
down
have one
here in
here,
the
sorry,
front.
yes.
in the-
Sorry. First, excuse my English. Then, what I want to say, it's almost just for fun. As a former Russian, not mission, but missile control, strategic missile control headquarter, night shift commander, I want to recall the animation. And there are a lot of scientific significance. But it is one more historical. It is the real first episode as a former military, Star Wars. Because we had a target and we hit it.
Yes.
It is historical event. It is not a science fiction. It is only for fun. Because as former military, I cannot miss it.
Yes. We did better than our own Defense Department. However, our target wasn't trying to avoid us either.
I told just
And an interesting point that didn't get said, but I think if you go look at the website, you'll see that actually it was the comet that hit you.
Yes, that's true. Strictly speaking, if you look at the coordinate system, the comet ran over us. But
coordinates and
You were just out wandering around and this
It
thing
doesn't
hit you.
matter, you know, how we do Star Wars, it is a little different than
Yep.
convention.
right.
So I think we have time
We call
for
it is just for fun.
another question. Where was it at? Was there? Sure, right here.
So you mentioned that the surface is similar to talcum powder. What's your guess as to what would happen if like a person stood on the surface?
Oh, I am not a fan of the famous Tommy Gold theory of the astronauts on the moon sinking over their head in dust. You step on it, it will compress, and it'll compress fairly quickly till it gets enough strength. Remember, it only has to hold you up against this negligible gravity. So you'll step on it and you'll be okay.
Wear snowshoes.
Yeah.
So if there's one more question, we'll take it.
If this core is just a, blob of gas, essentially, or powder.
Dust.
Powder, dust. Why doesn't it have a spherical shape?
Because there's been differential outgassing from different parts of the surface, so you erode away the surface by different amounts in different areas at different rates of sublimation. That's one reason. Second reason is that it doesn't have a spherical shape because even though it's incredibly weak, gravity still isn't strong enough to overcome that and make it spherical. If you have real rock, you've got to get up to 500 kilometers before it'll become spherical. You know, these you probably have to get up to 20 kilometers before they become spherical.
So part of that is because where you started in the beginning, it's how it came together.
Yep.
Pieces of Play-Doh that stuck together over a long period of time, and it didn't start out as a sphere. That's why it's not a sphere. Is that correct?
Yes, that's correct.
I learned something today. And we have another question. We're going to keep them coming.
This comet is spinning, of course.
Yes.
How stable is the spin angular momentum? And in particular,
In units of h-bar.
Really big.
given how stable it is, given that the moment of inertia changes as stuff evaporates unevenly, as you just mentioned, and also, is there any chance that one can actually observe the change in the spin angular momentum because of the impact, or is it beyond measure?
Okay. Which piece to answer first? 10 years ago, when we were first meeting about this, I was trying to convince the rest of the team that measuring the change in the spin period after we hit it was a perfect way to measure the moment of inertia. In principle, the change is big enough but in fact, we don't know the momentum transfer efficiency well enough to do it. As far as we know, the comet is in, over the last 10 years, is in simple principal axis rotation. There is some evidence of a slight change in period between when we observed it in early 2004 from Hubble Space Telescope and the Spitzer Observatory compared to our approach data. But there are a lot of artifacts in that data, and we have not yet decided whether the apparent change in period from 1.711 days to 1.698 days, we're not convinced that that's real. We're still working on that. So there may be a chance to measure it over the time scale of 100,000 years. The rotation period is certainly not stable, and the axis even isn't stable. Long-term simulations show that there's a tendency, due to the outgassing torques, for the comet to go to a state in which the spin axis points towards or away from the sun, right at perihelion. There's a tendency for that to be an end state.
Well, I'd like to take the time then to thank Dr. Ahern again for coming here and sharing these thoughts with us. I think I had a lot of fun listening to it and talking to him today, and it's great to see such a distinguished alumnus come back to BC, so thank you for coming back, and thank you for your attention here.